Hello and good morning. My name is Patricia Killen. I am a process development engineer from Gencoa Limited, and we are based in Liverpool in the UK. So today I am going to be talking about real-time spectral plasma analysis software tools. So just before we begin, let me introduce Jenkoa. So Jenkoa has been perfecting its range of microtrons and plasma deposition components for over 26 years now. So we design and manufacture cathodes from planar magnetrons to rotatables, ion sources, plasma treaters to process control units and gas sensing products such as the Optix and the Speedflow, which is what we'll talk about today. So the Gencoa Optix is a robust multifunctional gas analyzer. It is suitable for use in any vacuum environment. It creates a remote plasma and analyzes the spectral features and can be used in various modes such as RGA or OES, and applications include air leak, so to detect if your chamber has a leak, endpoint etching, endpoint detection for etching, atmospheric sampling, roll-to-roll, whether it's plastics or metals, ALD, so atomic layer deposition, and feedback monitoring. So the Jenkoa Speedflow is an advanced reactive feedback control system. It helps with deposition rates, coating properties, and process reliability. It is designed around the demands of real processes in the industry. And there are two options. So there's the Speedflow, which has 8 channels, and the Speedflow Mini, which has 3 channels, and it has the flexibility to benefit a wide range of reactive processes from magnetron sputtering to plasma enhanced CVD deposition. So there are various configurations that you could have the Optix. So the top left is the standard package. So that is the Optix with the plasma generator, with the power supply, which is DC, but you can have DC pulsed as an option, with the spectrometer head and the Optix software package. Or you could have the standard package, but with the optional optical fiber link between the sensor and the spectrometer. So this just increases the flexibility of the package. Alternatively, you could have the plasma generator with the power supply, and this generates an intense plasma over a wide pressure range, and you can link this to a Speedflow or other control platforms. Or you can have just a spectrometer head, and this lets you take advantage of this Optix software, which can help you manage your plasma monitoring. So why you would use the Optix is to identify process problems during deposition. It can detect issues such as faulty MFCs, so if your MFC isn't closing and gases are leaking through, contamination such as organic contamination, outgassing of your substrate or chamber walls, and leak detection. So the helium leak detector is obviously a very common piece of equipment in the vacuum industry, but the Optix can also be a very useful tool to detect an air leak. So if there is water vapor, oxygen or nitrogen present in the system, this will be shown in the spectrum, and this will give you an indication on whether or not you have a leak. Process control, so the Optix looks at the residual gas in the process and uses this information as a sensor. And the spectrum, along with the pressure gauge, which is now implemented on the new model of the Optix, provides a partial pressure of the relevant gases. If you pair it with the Speedflow, then it's very good for feedback control. So the Optix would collect data on the reactive gas, acting as a sensor, and the Speedflow controls the MFC, so the actuator, and ensures that the required amount of gas is being fed through to the system. And this is just guaranteeing full process control. And the principle for the Optix is the remote plasma emission monitoring. So what it is the Optix is attached onto the side of your vacuum chamber. It creates the remote plasma and collects the information, which is fed through the miniature spectrometer, and then the spectrum is displayed on our very sophisticated software, which will automatically identify the species present in the system, giving you analysis of the species composition and concentration. So current issues. So currently there is a lack of dynamic range with the Optix. So we're going to talk about integration time. So integration time is proportional to sensitivity. So it's how much light is being collected at that one time. So at the minute, we are unable to measure very large signals and very small signals simultaneously. So if we want to measure the large signals, we would have to use a lower integration time. And if we want to look at the smaller signals, we have to use a high integration time. But at the minute, we can't do both at the same time. So this is depicted here. So on the left, we have low integration time of 20 milliseconds, and you can see the detail of the larger signals. And then on the high integration time, 315 milliseconds, the lower signals are amplified, so the intensity is increased, but we start to lose detail on the larger signals as those peaks have been saturated. So to overcome this, we have added a new feature into the Optix, which is the HDR mode. So in order to obtain the best data, we use HDR mode, so high dynamic range. So we do this by using a mixture of integration times ranging from small to high. We obtain information from the spectra with different integration times, and we can exploit the linear relationship between the signal and the integration time to calculate the peak height beyond this saturation point. So it's very similar to what is used in HDR photography. So this is usually an option in more recent phones and cameras, where a photo is created by capturing multiple images with different exposures at the same time. So this is another example of HDR mode in photography. So you can see that there is 6 images captured at different exposures, or the same image captured at 6 different exposures, and the combination of them give you the high dynamic range photograph on the bottom. So it's a crisp, clear, detailed photograph. And that same concept is what we are applying to the spectrum. So we take the same spectrum at various different integration times. So we start with a low integration time of 20 milliseconds, and you can see the detail of the larger signals. And then we increase them to 125, we increase the integration time to 125 milliseconds, and then again to 315 milliseconds. And as that integration time increases, so does the intensity on the y-axis. So we are able to amplify the detail of the smaller signals, but we start to saturate those larger peaks. So to overcome this, we do the same as the photography. We take various different or multiple different integration times, and we combine them to create our HDR spectrum, which is this. So this is what we're left with. So it is a full spectrum, no saturated peaks. The intensity has been increased, and we have just combined the spectra, taken at the multiple integration times to provide us with this final HDR spectrum. So HDR mode versus high integration time. So this is our HDR spectrum overlaid with our high integration time spectrum. So the high integration time is what we usually have, or what we had before we had the HDR mode. So you can see that the smaller signals aren't changing between the high integration time and the HDR mode. But you can see in the high integration time where those larger signals would start to saturate. And with the HDR mode, we are able to extrapolate that data and reconstruct those peaks, so we're not losing any of the information. And the same for low integration. So HDR mode versus low integration. This is the same graph, but we're focusing on 350 to 450 nanometer wavelength. So this is what we would have with HDR on the top right, versus the low integration time. So you can see that the signal to noise ratio has been greatly improved in HDR mode, and you just get a far more clear and detailed spectrum. Another new feature of the Optix is the Automated Spectral Identification. So our spectrum is identified in real time on our software, and we do this by identifying the peaks, so the wavelengths of each of the peaks, and we can filter that using species identification, which converts wavelengths into the gas species that they correspond to. So the database is so large, so very frequently you end up with multiple matches for the one peak. So to overcome this, so it can be a very busy spectrum looking at it. So to filter this even further and to get a clearer overview of what's in your system, we can use unique filters, which removes the duplicates. So it removes any peak, it doesn't remove it, but it removes any identification for the peaks that have multiple matches. and it simplifies it down so that only the peaks with one match are being identified on our spectrum. And we can take this even further with max filters, which in this case, we only identify the largest peak for that gas species. So say you had nitrogen in the system, it would take all other nitrogen peaks away and only have an identification on the largest peak. This wavelength for the largest peak is then automatically exported to the species list in the Optix. So this is a video just showing the software being used. So here we have oxygen, argon and nitrogen flowing. So you can see at the top we click Auto ID and that brings up the wavelengths corresponding to those peaks. So you can see that it's very colourful, but it's very busy and it's throwing too much information at you. So we can filter this by clicking Library there at the bottom, and that brings up the gas species for those wavelengths. And you can see on various peaks there's multiple matches. So we use the unique filters to filter that down and only have the peaks with one match being identified. And then even further, we can click Unique Max, and that identifies only the highest peak for nitrogen, the highest peak for argon, and the highest peak for oxygen. So it's just a far more simplified spectrum. And you can see as we compare it, so this is what we had before, a very busy spectrum with multiple matches per peak, down to just identifying the three gases that you have in your system. So we can measure these highest peaks, so we can find out the exact wavelength of each of those peaks. So that's it for nitrogen, that's it for argon, and that's it for oxygen. And from there, those wavelengths are already automatically exported into the species list for the Optix. So you don't have to do this manually, this is all done for you. And just to show, whenever we go into the species list in the Optix, there is the wavelengths. So that is the automated spectral analysis. And some conclusions from today. So the Optix is a robust instrument, very useful for helping you perfect your process for gas sensing, and is suitable for any sort of vacuum environment. The Speedflow can assist with a wide range of reactive processes, and some new features of the Optix are the HDR mode, which gives us the benefits from both low integration times and high integration times simultaneously, and the automated spectral identification. So we're simplifying the data expressed on the spectrum all in real time. So that is everything from me. So thank you very much for your attention. If you need any more information, please go to our website, www.genkoa.com. My email's on screen, so feel free to get in touch, and I hope you have a lovely day. Thank you very much. Bye.